Okay, so again, starting on page 41 today. First, I'm going to make an announcement, and it's going to be very strange because I'm going to stare at that back wall while I make this announcement, so nobody thinks I'm talking to them. The last day to withdraw from any class here at GCC is this coming Friday. So if you are thinking about withdrawing from this class or any other, talk to your advisor. If it's this class, talk to me. But Friday, end of the day, end of the business day is the last day to withdraw this semester. Any questions on that? If you withdraw, it would show up as a W on your transcript, but that would not count. It wouldn't count in your GPA. Other questions on that? Yeah, I used to make that announcement and make eye contact, and people would be like, "Why are you staring at me? Are you telling me I need to drop?" And, all right. So, okay. So our quick look at the calendar tells us that the apportionment project is due today. I got a number of them in my email over the last 24 hours, which is great. I think that technically it is due by midnight tonight, so it's not late just yet. But if I don't get it until after midnight tonight, then the penalties start accumulating. And I think I have to go back and look at the syllabus, which you guys have, but I think the penalty is -5 per school day, even on days that we don't meet. So if you don't get it to me until next Monday, because that's our next class meeting, then you are Thursday, Friday, Monday, 3 days behind, which is 15 points off. So you want to get it in as soon as possible, even if it can't happen by midnight tonight. Okay, so today we continue on with population growth. Last class we saw things that were all linear. This class we see things that are exponential. We'll define what that means. After today, Monday is our last day of new material before test number 2. Wednesday, a week from today, is our review day. And then Monday, the 17th of November, is our second test. Questions on the calendar? Okay, so we will start on page 41. Okay, can we start with Ashley for number 1, please? Okay, thank you. So the idea last class was we kept adding the same number over and over again. Let's go to Christopher for 2. Okay, so the main idea for today is that every time we multiply by something to get to the next number. So I direct your attention to the bottom row of the blue numbers here on the wall, starting with the 2, and then 4, and then 8, and then 16. What are we multiplying by each time? 2, right? Multiply by 2, that brings you next to the next number. So what kind of a sequence is that? It is a geometric sequence, and it is something called exponential growth, okay? Where you just keep multiplying by the same thing over and over again. All right, let's go to Megan for 3. Okay, so let's try this. Again, starting with 6 billion people, which is about what we had back in the year 2000. Population doubles every 45 years. Let's write down what we have in 2045. So how much will we have then? 12 billion, because we double the one time, right? So I'm just going to write that as 12B for billion. And the next year we ask about is 2090. So again, it's every 45 years we double. So somebody else, how much do we have in 2090? It's 24 billion. And then we jump way out to 2450. So what we want to do is get the answer without actually listing all the years in between that we've skipped over. So the question is, how many doublings will we have? So the first doubling happened at 45 and the second doubling happened at 90. Can we calculate how many doublings we've had up until 2450? Tony, what's your idea?
What I did was, since it's 2000, 450, so I divided that by 45, which is like
Tony says 10 doublings. Agree or disagree? Everybody hear the rationale? Need to hear it again? So is it sound or is it flawed? What do we think? One thumbs up. All right, there's 450 years elapsed. Another thumbs up. Every 45 years, something happens. So the something has happened 10 times. Division is absolutely the right thing to do. So then 10 doublings. Okay, let's see. So we started with 6 billion, and then we double 6 billion to get to 12. Then we double again to get to 24. Then we double again to get to 48. Double again to get to 96. Double again to get to 192. That's 5 of them. We got 5 more to go, and I'm kind of running out of the ability to double these things in my head. So how about we do something a little bit more efficient than that? Doubling 10 times really means this list of operations, right? 1, 2, 3, 4, whatever, however many doublings we have. If I just multiply by 2 10 times, that's what we're saying we're doing here. And you guys have a nice shorthand way to write down repeated multiplication by the same number. It's exponent, right? That's what an exponent is. So I don't know how many 2's I have there, but really 2 to the 10th is going to capture doubling 10 times. So all we got to do is come back over there and we put our 6 billion that we started with and multiply it by 2 to the 10. Yeah? And this is something our calculator can do. Also, because I'm so smart, I think I can do this too. Let me see here. 6 carry the 1, 2, 3. Kind of losing it. That. $120, $136. Am I anywhere close? 144. Anybody else get 6144? Do we know how to do this on the calculator, gang? 6 times 2. The power button often looks like a caret, like an up arrow type thing. Where is it on mine? Also looks like this, x to the y. You see that? It's kind of small, but 2 to the 10th power, 6144. Good? 6144 people. Billions of people, right? The unit has been billions this whole time. Okay, that could be problematic. I don't know what the capacity of the Earth is, but I'd be surprised if it was that big. And then the same kind of game up here with 2900. So we take Tony's idea. How many years elapsed between the start of this experiment and 2900? 900 years. And then we're trying to figure out how many doublings. So what do we take that and divide by? It's the same 45. And that means 20 doublings. And so what's the thing that we're going to type into the, what are we typing into our calculator then? 6 times 2 to the 20, right? It's like 6 million and change. 6 times 2 to the 20. 6, 291, 456. 6, 291, 456. Okay, that is billion. So let's get some zeros out here. 1, 2, 3, 1, 2, 3. Anybody know the name of that number? 6 what? It is not a Google. 6 to the, or 6 what? So we go millions, billions. What's after billions? Is trillions. And then the next group after trillions is, yeah, tri for 3. So quad for 4. So quadrillion. We need a word that means 5. Quintillion is good. So this would say 6 quintillion and change would be the number of people on Earth. So yeah, This is kind of what happens when things grow exponentially, is we get these like massively large numbers very quickly. And you think about the span of like the history of the Earth, you know, the 900 years that we're talking about isn't all that long. It's long to us, like it's far longer than a lifetime. But in the context of the history of the Earth, 900 years, not all that long. And so if the population doubles, is there a question back there? If the population keeps doubling, keeps doing the same thing like every 45 years, we get these absurdly large numbers, like mind-bogglingly large numbers. And this is kind of what makes like all the global warming stuff scary. And if you ever see any of those graphs, you know, like it hardly matters what they're measuring. It seems like all the graphs look like this, right? All the graphs look like that. So carbon dioxide content as time passes, or population, or temperature, or whatever. They all look like that. And this is what the graph looks like when you have something like this, exponential growth, where it keeps doubling every 45 years, say. Yeah, okay, so let's keep going with this Earth's idea. Sarah, number 4. Okay, so let's try this guy. 1955 was chosen very particularly. Relative to 2000, we've heard from Tony, who can tell us about 19. It's 45 years earlier, right? The population doubles every 45 years. How can we go back? We can divide by 2, right? If we're doubling going the one direction, then we should be halving going the other direction. So 1955, we just have to take half of what number? Half of the 6 billion that we start with, and we end up with 3 billion. Super. And then if we go back to 1820, I think we need Tony's trick again, right? We need to figure out how many 45s have elapsed. So let's see, how many years have elapsed between, it's 180 years. And we'd keep dividing by that same 45. We get 4, we've been calling it doublings, but I guess if we're going the backwards direction, 4 halvings, right? We have to half the population 4 times. And so we can half the population a few more times, and then I think we'll need a calculator, but let's see. So we went from 6 to 3, and then from 3 to 1.5, which is half. Half of 1.5 is 0.75, and then half of 0.75 is 0.375. That's 4 halvings. So I think that's our population here. 0.375 what? Billion, which is really 375 million. Tony? Yeah, better known as 375 million, right? Okay, but then when we get to the last question in this group, I don't think we're going to be able to count out on our fingers like we just did on the previous one. So 1100, we play the same game. How many years earlier was that? So that's 900 years ago. Divide that by the same 45. It goes in 20 times. So that means we're doing what 20 times? We're going to have this number 20 times. So 20 halvings, I guess we can call it. Okay, so then we'll take our 6 billion people that we started with, and then instead of multiplying by 2 to the 20, divide by 2 to the 20. Isn't that going to take care of it? Divide by 2, divide by 2. That's halving something. Okay, and so we can do this on the calculator. So what are we doing here? Let's see, 6 divided by 2 to the 20, 2 to the 20. Yeah, because 2 to the 20 is a massively large number. In fact, 2 to the 20 is this last blue number over there. You guys told me that was the doubling list, but it's also the powers of 2 list. So 2 to that 20th is a million and change. So if you take the number 6 and you divide it by a million, you get something really close to 0. So it's this many billions of people, but we can make this number easier to work with because it's billions, and that's not the best unit for that number that's so close to 0. So I'll just copy it. How many zeros? Is that 5? And 5722 and change. So is that many billions of people? So more testing of your ability to name the numbers. If I go 3 places over, I would now be talking about what unit? It wouldn't be billions anymore. It would be millions. 1, 2, 3 more over gives me thousands. So it seems like about 5,722 straight people, right? 5,000 and change. And so this kind of gives a little bit of credence to stuff that I've heard before, like there are more people alive today. You guys heard this thing before? Than what? Than what about ever before? Than like have ever lived for the rest of humanity, right? There are more people alive today than all the people in the world that lived and died before. Okay, well, it's not so hard to believe if we're not going back that far and we're only talking 5,000 people, and now we're talking 6 billion. Actually, I think we're above 7 billion now, right? So it's not so hard to believe. Okay, number 5, let's go back to Jen. Okay, 2120. Let's use Tony's technique. It's carried us pretty far so far. So 2120, we figure out how many years we are from 2000. It's 120 years. And then what do we do with that? Divided by 45. And with the disgust in your voice, you see that that doesn't go in evenly, right? Zeke, what'd you get? 2 2/3. 2 2/3 what? What is that counting? That's the doublings, right? We've been looking at doublings this whole time. So 2 2/3 doublings. I understand how to double something twice. I don't understand how to double something 2/3 of a time, right? It doesn't have meaning. But yeah, I mean, let's just try the same thing that we did before. 6 times 2 to the, we put a 20 up here. What could we put up here now? Can we try putting that 2 2/3 up there? Like even if we've never seen that kind of a thing before, like that's what it looked like when the numbers were nice. And so we're not going to get into what this means, that 2 2/3 power, but the calculator didn't bat an eye. What is it? What'd you get? 37.92. Let's see if this makes sense. We don't have to know what 2 2/3 means to decide whether or not that answer is reasonable. If we double twice, we start at 6 and we double twice, what do we land on? Double twice. So we land on 24, right? 12 and then 24. If we double a third time, what do we land on? 48. So if we are doubling 2 2/3 times, something between 2 and 3, are we buying that it should be something between 24 and 48? And it is. So without knowing what 2/3 means as a power, at least this is reasonable. If you want to know what 2/3 means as a power, see me after class. I'll tell you it's not hard. It's not what we're after today. But in any event, it's kind of nice to use the same technique, Tony's technique, even if we get powers that aren't perfectly nice integers, right? Okay, let's move on to 6. Jeff. Okay, so we'll start with a rabbit population. I'm going to call it P0 equals 1,000, just using the same notation we did last time. And we're going to increase by 20% per year. So how many new rabbits do we get in the first year? 200, right? 20% of 1,000 is 200, plus the 1,000 rabbits that we already had. So now we're up to 1,200 rabbits. And then we gain another 20%. So is that another 200 rabbits? More or less than 200 rabbits? Why more?
Because it's 20%.
That's it. It's 20% of the new number, right? So we're going to get 20% of a bigger number. So it's going to be bigger than the 200 rabbits that we gained before. Anybody know what 20% of 1200 is? It's 240. Yeah. So 20% of that number is 240 plus the 1200 we had. That gets us to 1440. All right, so this idea, and I haven't written the details down because I actually don't even want you to do it this way. The calculations get a bit cumbersome, and then it doesn't really put us in any place to do a formula for n, because all we're doing is saying, well, I guess we could write a recursive formula. Could do that. But even then, like, how do you say, like 20% of this number that I can't really refer to explicitly? So an alternative to this idea of find 20% of the old population and then add it is as follows. If you start with 100% and you gain 20%, then what percentage do you have altogether? Start with 100% of something and you gain 20 more percent, then you have what percentage? 120, yeah? So this problem could be reframed to say, not that you gain 20% every year, but that you end up with 120% of what you had every year. And so that's how we're going to reframe this. 120% of the previous year is what you'll have in the next year. And so I'm going to erase these numbers, and then we're going to get them in a nicer way. So we took the 1,000 rabbits that we had. What decimal is 120%? 1.20, right? We know to move the decimal twice. And how would I find 120% of 1,000? Just by that, that means 120% of 1,000. And so this one we should be able to do without a calculator, right? Just move the decimals a couple places and we'll get the same 1,200 we got before. But the nice thing is that we can then play the same game with the 1,200. What should I multiply it by? 1.2, which is just 120% of what you had before. And so if you type that on the calculator, you're one step ahead. We'll get that one down next. But this one is 1440. And we'll do one more. 1.20 times what new number? Somebody with a calculator who's got this number? That's our 1728. Okay, so I think we can now write down a formula for this n years away. At the moment, our technique always relies on using the previous number, right? We use the previous population to get the next population. So is that the kind of thing that works with an explicit formula or a recursive formula? That's a recursive, right? Because we keep using the previous number. And so we know that our recursive formulas generally just start Pn equals Pn minus 1, right? That's what it looks like. What did we do from one population to get the next? Multiplied by 1.2. So I'll put it in the front here, 1.20 times. That's it. That's what the notation means. We talked about this notation last time, and in plain English, and that's what I'm really interested in. It's not the specifics of this calculation that's interesting, but in plain English, I want you to be able to read that sentence and say, oh, you want to know what the current population is? You take 1.2 times the population from 1 year ago. Last year's population times 1.2. And then remember, we also had to list the initial amount. So those two things right there form the recursive formula. But it turns out there's an even nicer way to talk about this guy. And that's using an explicit formula, which we'll do right here. Pn equals. Okay, again, what did we multiply by every time? 1.20. And so the 1200 was 1.20 of the 1000. Okay, that's what that equation says, but let's look at the next one. That 1440, I know it's a 1.20 times 1200, but I want to know how many 1.20s will get me from 1000 to 1440. How many times did we multiply by 1.20? Twice, right? And if I'm trying to get from 1000 to 1728, missing an equals here. How many 1.20s did we multiply by? 3. And repeatedly multiplying by 1.20, again, we have a nice shorthand way to write that. How do you write multiply by 1.20 3 times? I want to know how we write it. How do we write in shorthand multiply by 1.20 3 times? 1.20 to the third, right? And it's the same exponent we talked about before. And so if, again, you have a calculator out, if you type in 1.20 to the third times the original 1000, you will immediately get that 1728 without going through the previous calculations. So those two are the recursive formula. And our explicit one is take 1.20, raise it to the right power, which is exactly whatever that little subscript is, and multiply by 1000. So I'm hoping we can make the connection between that thing and this thing right here. Take 1.20, just raise it to the right power, which is however many years we've been in, we've gone down the road, and multiply by 1000. What kind of a formula is this one? What do we call it? That's explicit. All right, our next reader is Zeke, that little part at the bottom, the number. Okay, so I'm going to write down a couple of calculations that you don't need to do, but I just want to verify something here. If I take 1728 and divide it by 1440, I'm going to get something. If you really think about it before touching the calculator, you should be able to figure out what you're going to get. Same idea over here. If I take 1440 and divide by 1200, it's just one population divided by the previous year. Can somebody type this on a calculator for us? Or tell us what they expect to get. That says probably 1.2. And it is. Of course it is, because you get the bigger number by multiplying the small one by 1.2. So if we divide, we'll get right back to the 1.2. So just like last class, we had the phrase common difference, right? We keep adding the same number over and over again. We called that the common difference. Here we call this the common ratio, because when you take the ratio of two consecutive populations, you keep getting that same number, the 1.2. So I'm going to ask you guys to go to the next page. I'm going to keep the previous formulas projected just so we can make some comparisons. But we just figured out how to write this example using recursive formulas and using explicit formulas. But they are listed there at the top, but you don't need to memorize it. But let's make sure we see that they're the same. Which one is first, recursive or explicit? Recursive, and it says Pn equals Pn minus 1 times what? The common ratio, and I just want to make sure that we're clear that that's exactly what this equation right here says. Pn equals Pn minus 1 times the common ratio, the 1.20. Yes? And then the very next formula is the explicit one. What does it say in English there? Pn equals? On the next page, I want the kind of generic formulas at the top. Tony. Not always squared, but I'm hoping that's an n up there, to the power of n. Okay, so it says whatever you want to get, you take your starting amount, which was 1,000 in this case, You multiply it by the common ratio, which is the same 1.20, and you raise it to the n. These two guys have to match up. Don't need to memorize the formulas. You'll have them in front of you on the test or on the homework as long as you put them on a study sheet, but they're there just in case you need them. Okay, next page. Let's take a look at problem number 8. Who's our reader now? Is it Matt? Okay, here are your two choices. You could either have a check right now for $1 million, or you could have a bank that follows this really strange rule. Starts with a penny, and every day it doubles, and at the end of 30 days, that's how much you get. So the question is, which one would you rather have? So one vote for the doubling. Take $1 million. You could. You get it before the 30 days are up. That's true. How about we do the math first? Let's do that. All right, let's do the math. Okay. There's one word in this problem that tells us that we should be doing this. It tells us these formulas are in play. What's the one word in this problem that says we're doing one of these exponential growth things? Is doubles. That's the key word. So that word right there means, oh, we're in exponential mode. And so let's use the explicit formula. It's easier. So the formula says Pn equals, what's the starting amount for the doubling problem? 1 cent. So how about we do this as a 0.01, so we'll keep it in dollars. So we start with a penny. And then that's the start amount, and then times the common ratio. What is the ratio if we're doubling every day? It's 2, right? Every day is 2 times the previous day. So that is multiplied by 2 raised to what power? It will be 30 in a second. I'm going to leave it as an n just in this formula. So are we clear that that translates to that? Any questions on any of the pieces? Okay, so then in particular, we're interested in knowing how much money we have at the end of 30 days. So we just copy that entire formula, but n becomes 30. Now again, even without a calculator, we at least have the blue numbers on the wall here. So this million number right here, that's after how many days? 20, but this assumes we start with one what? With $1, which is not what we're starting with. We're starting with a penny. So how do we take this number and make it into our problem? Divide it by 100, right? Because we're starting with 100th of what this sequence started with. Okay, so that's 1 million. Divide by 100, so the 0 moves twice. 10,000 and change. All right, move the decimal over 2 places to the left. So 20 days into this experiment, you'd have about 10 grand, which is a far cry from $1 million. So maybe we're not doing so great, but we have still 10 more days to double. 10 grand becomes 20, and then 40, and then 80, and then 160, and 320. So we're already at 320,000, still with 5 days left to double. So maybe, Tony, you're changing your mind? All right, so let's see, 0.01 times 2 raised to the, nope, 2 raised to the 30. All right, what is that? It is. It's how many million? Is it 1 million or 10 million? 10. 10, 7, 3, 7, 4, 1, 8.
Way to go. Had to make it really quick.
All right. Okay, so a couple of observations about this last one. First of all, once you have the formulas in front of you, these problems become pretty quick, right? They're really straightforward. So really, we spent the bulk of our time today just kind of getting a feel for how the formulas might come out. But now that we've got them, the problems become pretty straightforward. the other thing, and I've read this in a couple of places, somebody has said that humans are just not designed to understand exponential growth. We just aren't wired to be able to predict long-term doubling like this. Because everybody was surprised that it was $10 million, right? From a penny to $10 million in 30 days. And that's just 30 days. And so, like maybe it's not such a shock that we were surprised because we're just not wired to understand this kind of exponential thing. Okay, so last piece of reality and then the group work. Where's our reader now? We'll come up here to Ricky for 9. Okay, so this is more realistic because as Ricky read, like their resources for people are finite, right? And so at some point we'd run out of food or water or something if there were too many of us around. And so oftentimes you get this kind of cap or capacity at the top, and it's just like the planet won't sustain more than this many people. So that's a much more realistic model. Of course, the equations for this kind of thing are more complicated than the equations at the top of this page. We're not going to study them, but if you are interested, just look up logistic growth online and you will find plenty to read about. So the activities on the next page, a bunch of it has to do with bacteria. I think what we're going to do is plan on coming back together in about 15 minutes because next class is a little bit long, and it would be great if we could get a jump start on next class so we don't feel like really rushed next class. So do as much of this activity as you can in 15 minutes, and then we'll come back together a little bit before 2. Okay, so we're at the top of page 45. Like I said, we're gonna make the next class a little bit shorter because it's a bit long by doing a bunch of it or a little bit of it here at the start today. Ricky, did you read? Monica, can you read that first part? Not all.
Not all populations follow a linear.
Okay, and then jump down to the female bees. Okay, so what we're going to do is talk about this bee problem. So it is true, sounds strange, but quite true. Every female bee has 2 parents, a mother and a father. But every male bee came from an unfertilized larva, which means the male bees have only a mother. The male bees do not have a father. You got it? Sounds very weird. It's not how we do things, but that's how bees do. So looking at this family tree, we are going to look at the genealogy of a single male bee. We're just going to trace this male bee's ancestry, right? Parents, grandparents, great-grandparents for a while. So male bee, how many parents does a male bee have? Just one, and it is always what kind of a bee? A female bee. And so that is what's drawn there. Every female bee has how many parents? 2, 1 male and 1 female. And that's written there, okay? And then we go down the next row. I'm looking at this male bee. How many parents? Just 1, and it is a female. And the female bee has 2. So your task is to start filling in very carefully. You don't need to put my little line segments, but you need to put F's and M's very, very carefully. And once you've filled in all the F's and the M's, you are going to fill in the last 3 columns, which asks you to count total bees in each row, total female bees in each row, and total male bees in each row. Maybe start filling in some of these numbers before you get too far, and then check in with your neighbors. We want to make sure everybody's doing the right pattern. So fill in generation 5, count the bees, check with your neighbors.